4 planets in our solar system once had, or still have, conditions that scientists consider potentially habitable. Mars, Venus, Neptune. 3 worlds so different from Earth, yet each tells a story of water, atmosphere, and maybe life. Habitability is not permanent. A planet can be friendly for 1,000,000 years, then deadly for billions. The classical habitable zone is defined by liquid water on the surface, but life may exist beneath the surface or in clouds. Earth taught us that life finds ways. Extremophiles survive boiling water, acid, radiation, and vacuum. The habitable zone is larger than we once thought. We have sent orbiters, landers, and rovers to Mars. Each mission brings us closer to answering one question: was there ever life? Venus is Earth's twin in size, but not in temperament. Yet radar images reveal a past that might have been much cooler. Neptune is an ice giant, freezing cold, no solid surface. But its moon Triton and its deep water ammonia ocean raise unexpected questions. 3 planets, 3 different environments, 3 separate investigations into the possibility of past life. We have only one example of life in the universe, Earth. But that example tells us clearly, life emerges when conditions allow. "4 billion years ago, Mars looked very different. The atmosphere was thicker, the sky was blue, and water flowed freely. Jezero crater once held a lake fed by a river delta. Perseverance rover is currently drilling into those ancient sediments. Curiosity found mudstones at Gale crater, formed in ancient lakes. Lake water that was neutral, not too acidic, and had all the chemical elements life needs. Organic molecules have been detected on Mars. Not proof of life, but the building blocks were present. Mars releases methane seasonally, more in summer, less in winter. On Earth, most methane is biological, but geological processes can also produce it. Liquid water still exists beneath Mars's surface, in deep aquifers and as brines that freeze at lower temperatures. The ALH 84001 meteorite from Mars contained tube-like structures resembling fossilized bacteria. Most scientists now agree they are not biological, but the debate taught us caution. Perseverance is collecting samples for return to Earth. Only laboratories here can definitively test for fossilized microbes. If life ever existed on Mars, its fossils may survive just beneath the surface, or deep underground where radiation cannot penetrate. Venus is almost exactly the same size and mass as Earth. It has an atmosphere, but that atmosphere is 90 times thicker and 900 degrees hotter. Climate models suggest early Venus had liquid water on its surface, possibly for up to 3 billion years. As the sun grew brighter, Venus's oceans evaporated. Water vapor is a greenhouse gas. More vapor meant more heat. A runaway greenhouse effect followed. The ratio of deuterium to hydrogen on Venus is extremely high, meaning most of its original water escaped to space. Venus lost an ocean's worth of water. 50 kilometers above Venus's surface, the temperature is 40 degrees Celsius. The pressure is 1 Earth atmosphere. Could life exist? In the clouds? Earth has bacteria that survive in concentrated sulfuric acid. Venus's clouds are made of sulfuric acid droplets. The chemistry is hostile, but not impossible. In 2020, scientists reported phosphine, a potential biosignature in Venus's clouds. Later analysis showed the signal was likely sulfur dioxide, but the possibility remains open. Venus's clouds contain unknown UV-absorbing particles. They could be mineral dust, or they could be microbes adapted to the cloud environment. NASA's DAVINCI Plus mission will plunge through Venus's atmosphere in the early 2030s, directly sampling cloud particles and searching for organics. The surface of Venus is almost certainly sterile today, but the clouds and the upper atmosphere remain the most intriguing potential habitat in the inner solar system. Neptune is an ice giant, 17 times Earth's mass, mostly hydrogen, helium, water, ammonia, and methane. Beneath Neptune's atmosphere lies a supercritical water-ammonia ocean. No solid surface, but liquid, under immense pressure, and surprisingly warm. On Earth, life thrives around hydrothermal vents, in total darkness, under crushing pressure, using chemical energy instead of sunlight. Neptune radiates more heat than it receives from sunlight, suggesting an active interior. That internal heat could drive circulation in its water-ammonia ocean. Neptune's largest moon, Triton, is more immediately interesting for habitability. It has active nitrogen geysers and possibly a subsurface ocean. Triton orbits backwards, suggesting it was captured. Tidal heating from that capture could keep an internal ocean liquid for billions of years. Tidal heating and radioactive decay could provide enough energy for liquid water beneath Triton's icy shell, similar to Europa and Enceladus. Ammonia acts as an antifreeze, keeping water liquid at much lower temperatures. Organic chemistry proceeds differently in ammonia-water solutions, but it still proceeds. Neptune's rings and moons are poorly studied. Only one spacecraft, Voyager 2 in 1989, has visited. A dedicated Neptune orbiter could answer the habitability question. Neptune itself, the planet, is less likely to host life, but its ocean of supercritical water ammonia is not impossible. We simply do not know. 3 worlds, 3 different habitats, one shared question: did life emerge independently anywhere other than Earth? Mars was habitable on its surface for perhaps 500 million years, Venus for up to 3 billion years. Neptune's ocean, if it exists, has been liquid for the entire history of the solar system. All 3 have, or had, water, carbon, and energy sources. Mars had sunlight and geothermal. Neptune's ocean has tidal and radiogenic heat.